Welcome to the second lecture in this mini course, and I will introduce you to multi-parameter persistent homology. Right? So, yeah. Figure out where to stand. Yeah, I'll stand here. So yesterday, Agnese told you about simplicial complexes, homology, and persistent homology, which is a way of extracting topological features from a point cloud. And today I'll introduce you to multi-parameter persistent homology, which is a generalization of persistent homology that allows you to have more control of the topological features that you extract. So the goal of today is that you will have an idea of what multi-parameter persistence is about, and that you get a feel for how you could potentially use it in applications. And feel free to interrupt at any point with questions. So first I'll reiterate some of the ideas that Agnese told you about yesterday. So persistent homology. And the what you see here in the image, so on the upper part you see a filtration of a point cloud. And the idea with persistent homology is to extract topological features from a point cloud, a set of data points, which is like the problem that it tries to solve is to sort of introduce some geometry among these points. So if you just look at the data points as they are, they have a very uninteresting topology. It's just the number of points. And so what you try to do is you introduce some geometry, but you don't really know what geometry to introduce. So you look at a range of geometries and then try to extract information from this, and this is why we construct this filtration. And what we do with this filtration is that at each point, at each filtration value in this filtration, we compute the homology of this simplicial complex. And that will produce the topological information we're interested in. Oh, that's wrong computer. So to summarize, the first step of this pipeline is to go from your data to a filtration of simplicial complexes. Then what we do is we compute the homology of each simplicial complex in this filtration. And we collect all of this information into what's called a barcode that Agnese told you about yesterday. Here's an illustration of this process where we, on the top, see snapshots of simplicial complexes in this filtration, and on the bottom you see the barcode for different homological dimensions. So on the top, okay, what's the best way of illustrating this? Maybe here. So on the top here, so I think you should see my mouse here. You see the first snapshot we have of this filtration, and we have a number of components here. So the zeroth homology, which is illustrated by these red bars here. So we have a bunch of them that indicate that we have a bunch of disconnected components in our simplicial complex. And we have no bars of higher homological dimension because we don't have any cycles or any voids in this data yet. And now if we look at the second snapshot here, we can see that there has been two cycles formed. This cycle here and this cycle here. And this is illustrated by these two green bars here. So these represent these two cycles. And then we have 6 number of components. We have one big component here. We have 4 individual points, and then one small little component here. And this is illustrated by the 6 red bars here. Okay, and then as we increase, as we sort of grow the balls around our points, as we fatten the balls, and increase the number of simplices in our complex, it happens that cycles are filled up. So the bars they stop, and components get merged. So the zero dimensional bars they stop, and all the way back here in the filtration, we get our first bar of homological dimension 2. So this means that there has been a void forming in our data. And then eventually all the homological information dies, and we are left with just one big blob. And that's what you see here in this last snapshot. All right. So this barcode, this representation of the topological information in the point cloud, it's a complete invariant, and it is also a stable invariant of this of the point cloud. And this means that it's complete means that it contains essentially all topological information that we want. This is a mathematical statement, but in practice it means that it just contains the information we want. And it is stable with respect to perturbations, which means that if we perturb our data a little, we can predict how much the barcode will change. So it will only also change a little bit. And this is something you want in data analysis. If it would change a lot, if it would be unstable, it will not be usable in practice. But to be able to, yeah?
What sort of perturbations are you referring to? Are they merely, can you add or subtract nodes, or are they merely perturbations in the end set?
It's perturbations in the data points, so in the point cloud. So if you exactly, so if you perturb your points in the point cloud a bit, then the simplicial complex, it might change. But this invariant is stable with respect to such changes.
Okay, thank you.
All right. So to be able to talk about stability, we need a metric on our invariant, so on barcodes. And the metric I will introduce you to is the bottleneck distance. So yesterday, Agnese talked about bus assigned distances, and this is a type of bus assigned distance that is easy to think about because it has to do with just matching the bars.
Excuse me.
Yes.
It's like the team is not letting people in. Those who are online.
Sorry, say again?
There are people online
Yeah.
that wants to join, but they are not being allowed to join.
I cannot see anyone in the waiting room.
Oh, okay.
Maybe they have the yesterday's link.
Someone just said when the meeting starts, let people know you are waiting.
Yes, but there's a different link for today's.
For today, okay, maybe I'll send the link for today.
Yeah,
Okay,
yeah.
Thank you.
All right. So to compute the bottleneck distance, we simply match the bars of our two barcodes. So the pink one here, that's one barcode you have. So you have one set of data points that you compute the filtration, and you compute the barcode, and you end up with this. And then on the on the right here you have another set of data points that you compute the filtration and the barcode ends up looking like this. And you want to compare how similar are these two sets of data points. And then you can compare them by just matching the bars. So what you do is you just put the bars on top of each other like this, and then you try to match them as well as you can. Formally, this is this optimization problem formulated mathematically, but it essentially just says that you want to match as well as possible. And this is a distance on the set of barcodes that you can use to show this stability. So in words, we minimize the worst matching overall matching of these two barcodes, which are referred to as B1 and B2.
How well does this work when the number of bars differs between the pink and the green case significantly? For example, you have many more points in one of the data sets compared to the other.
Yeah, so exactly. So if you have more bars in the other barcode, then some bars will go unmatched. And that's fine. And that's just something that's just how it is. But so the smallest bars will then become unmatched, and they are just matched to the 0 bar. So and intuitively this also makes sense, because the small bars are considered sort of noise. You can consider small bars as noise. That's sort of the philosophy of persistent homology. And to compute this, there is a lot of software. Agnese will tell you next week about Irene, which you will use to demonstrate some computational examples. And there are also Ripser in C++ and DIPA and many other softwares. So this is just a small set of examples. And they all use different types of optimizations. So computing barcodes is essentially just Gaussian elimination of a special class of matrices, and you can use a bunch of different optimizations to compute this. And the software packages all implement some variant of a set of optimizations. And current software can handle millions of points, so fair amount of points. All right. So multi-persistence.
Sorry.
All right. Is it? Here. All right. So multi-persistent, multi-parameter persistent homology is what we will talk about today, and it's a generalization of persistent homology in the sense that you can get more control over the topological features that you extract. So, for instance, you can extract topological features which are robust to outliers in your dataset. This is one weakness of usual persistent homology, that it's sensitive to outliers. And you can handle other types of data. You can handle multi-modal data and time-varying data, which you also cannot handle with usual persistent homology. So, So first I'll try to give you some intuition into how multi-parameter persistent is constructed, because it's a different type of filtrations, and how you can choose the metrics and filters that you use to construct this, and give you some examples of this. In part 2, we'll talk about invariance. So one thing about multi-persistence is that you don't have a barcode, like you don't have a nice invariance in the same way. It's more complicated, and also the information that you extract will also be more complicated. All right. Do you have any questions at this point?
I might have a question. So, to my understanding, so far the material you have presented looks at the different homology classes of a data set.
Yeah.
And as such, it looks at, for example, how many, simply saying how many holes there are of different dimensions.
Exactly.
I just wondered, I mean, this is sort of discrete information. So, for example, if a hole disappears, that would be signified as one a shorter bar or one or more
yes.
bars in your barcode. I'm just so in other fields such as dynamical systems, which is also concerned with geometry and topological descriptions. Often this disappearance of holes is shown in a continuous way. For example, in bifurcation diagrams, when you have a parameter vary continuously and then you suddenly one of the fixed points disappears, which might correspond to a topological change. Is it a conscious choice in topological data analysis to go into more discrete description, and can you maybe reflect on what is the weakness of this as opposed to looking at with a more continuous lens? I'm not sure if my question is clear.
Yeah, so let me know if I misinterpreted your question, but I would say that those approaches are quite comparable, because in persistent homology, the parameter you're varying is the filtration value. So you sort of look how the simulation complex evolves along the filtration values as you increase the filtration, and you end up with these bars. It is that is in theory continuous, but then when we implement it in the computer, of course it's discrete. Was that an answer to your question?
So maybe I just thought about a different way of phrasing it. So suppose that you have a manifold with a hole in it, and then you start continuously forming that manifold, and then at the end you just remove that hole with the surgery. In the process of kind of continuously shrinking that hole, will your filtrations and the derived homologies be the same, or is there a way to recover somehow this continuous shrinking of that hole, or is it something you're completely oblivious to in this field?
That might be more tricky, because I think I get your point now, because the data is in itself discrete. I don't know about that.
Thanks.
All right, so let's continue. So the process of multi-parameter persistence is very similar to persistent homology, only that you compute different things, essentially. So you start with your set of data points, your data. You construct a filtered simplicial complex, you compute the persistence module, which is an algebraic representation of this filtration, of the homology of this filtration, and then you compute an invariant. So for one persistence, or usual persistent homology, this invariant will be the barcode. But here we have some other invariant that we will talk about in part 2. So we start with our data, which we call X now. This is our set of objects that we want to study. And we, instead of a single metric that we use to grow balls around our data or fatten our points, we now have several metrics. So you can think of the metrics as one being the Euclidean distance and the other being maybe a density function or something. And the goal is to have a clustering or like an extraction of topological feature space robust to noise and outliers. So this is something you can think of. And we do the exact same thing, like we construct a filtration of a simplicial complex, but now using R number of metrics instead of just one single metric. We compute the persistence module, so this algebraic object that I will tell you about, by computing, just as in one persistence, computing the homology of each simplicial complex in this multi-filtration. And then after we have done this, so collecting our homological information of each simplicial complex in this filtration, we want to extract some information out of this. So the persistence module is a complicated object, and it's not easy to understand what's going on. So we have to extract information from this in some way. And this is what we refer to as an invariant of this object. So here is an example of a filtration of a multi-filtration where we use two metrics. So we consider this point cloud in the plane in R2, and we will construct a filtration using the distance in x-axis and y-axis. So we'll try to write this so you can see it online as well. So we said that the distance in the x-axis see this. Is it very small? Okay, I'll leave that as it is and try to write bigger. So it's just the absolute value of the difference in the x coordinate. And the y distance it's just the difference, the absolute value of the difference in the y coordinate. And so when we use this, when we use these distances to compute our multi-filtration, so geometrically we no longer get balls around our points, we now get rectangles. And so in the first, so let's look at the first filtration value in this filtration, which is down here. So we refer to our filtration values now as the first coordinate being epsilon, which is here 0.2, and tau, which is also 0.2. So at this filtration value, since the filtration values epsilon and tau are equal, we get squares around our points, because what's included in these squares are every point which is of x distance 0.2 from this point. So this square has a side 0.4. And the same for the y distance. So it's a square of side 0.4. Okay? And if we go in the epsilon direction of the filtration, and this corresponds to the x-axis and the x distance, we will start to enlarge our rectangle in the x direction. So now we instead have epsilon equal to 0.5, and then we include points which are of x distance 0.5 from our point, and this corresponds to this this rectangle here, where the bottom side of the rectangle is equal to 1 now, and the vertical side of the rectangle is still 0.4. And the same thing for the y direction. So if we look at the filtration value here, which is epsilon 0.2 and tau equal to 0.5, we do the same thing, but in the y direction. So here we get the analogous thing, but with the rectangle rotated 90 degrees. And then in the final filtration value here, epsilon equals to 0.5 and tau equals 0.5, we again get squares, and you can see here how they intersect each other. Okay, so this is how we compute how we construct the filtration using these two metrics. So we just compute these rectangles around the points, and then the idea is to construct an edge between the points that have an intersecting rectangle. So this we do in the next step here. So down here for the filtration value epsilon equals 0.2 and tau equals 0.2, you see that we have no edges because none of the squares here intersected with each other. But at the filtration value here, epsilon equals 0.5 and tau equals 0.2, we do get edges between the points down here, and we get these two components. Because you can see that all of these rectangles, they have a non-empty intersection. So we connect these points. And up here we end up with a simplicial complex that also has a cycle and some filled-in triangles. Okay. Now one thing I want you to note here is that the filtrations for the different metrics are different, right? In the x direction we get these two components. In the y direction we get these 4 components instead. And then we combine them into this joint representation up here. Okay, so that's sort of what I mean with that we get more control over the topological features that we can extract, because we get more detailed information baked into the representation here. And what we end up with after we compute the homology of this multifiltration is a set of 2 persistence modules. So this is the algebraic representation of the homological information that we extract. And I'll explain what this means. So for the homological dimension 0, we count the number of components, right? And at the filtration value epsilon equals 0.2 and tau equals 0.2, we have 7 components. So here, these are 7 individual points. But when we move in the x direction and increase epsilon to 0.5, the points get connected and it results in 2 components. And that's why we have a 2 here. And in the y direction, we have 4 components. And then at the filtration value epsilon equals 0.5, tau equals 0.5, we only have 1 component. And that's why there's only 1 k here. All right. And now for the first homological dimension, and the first homological dimension, it counts the number of cycles in the signature complex. And we have no cycles until the last filtration value. There we had one cycle, this cycle here. And that's represented by this single k here. And this is an algebraic representation of this topological information. And what these things are, so at each position here in this grid, there is a vector space. So this k here, this k7, that's a vector space of dimension 7. And here we have a vector space of dimension 2. And this arrow here is a map between those, mapping the homological or the topological features between filtration values. And this is how we represent this mathematically. And this is the object that we study now in order to get some information out of this construction. All right. So those are sort of So an example of how you make how this construction works, and what you need to know in order to be able to use multi-parameter persistent homology in practice are three things. The first thing you need to know is that you need to choose the metrics that you will use on your data to construct the multi-filtration. So, and this will depend on your application, right? It depends on what you want to do. So, so here are some examples of what you might use. So Euclidean distance, mutual information, a density filter. You could also use time or whatever metric makes sense to your specific application. Then the multi-filtration is constructed, and it's constructed by constructing signature complexes. And there's not just one way of doing this. And this is more of a technical point, maybe, that you should maybe not worry about too much. But depending on your type of data. So if it's time-varying data, then you would need to have a special type of filtration constructed, for instance. And so this is maybe something to keep in mind. And the last thing is that you need to know how to, like what invariant to look at for your data and how to interpret the results. So this is maybe the trickiest part. And this I will talk about in part 2. Okay, so the first thing, so choosing metrics. So I will now give you some examples of metrics for three type of applications. And the first one is clustering. So here, to make the clustering robust to noise and outliers, we will choose the Euclidean distance, which happens to be natural for our application, and a density filter on our set of points, which we here denote by FD. This will result in a two-parameter module, because we have two metrics, right? And so this will construct just as in our examples with the x and y distance, we will get a filtration parameterized by two filtration coordinates. And the density filter, so this is one example of a density filter, just to give you some idea of what I mean by this. There are many ways to define a density filter, but this is maybe one of the easiest. And it essentially, so you would choose some k, and you would look at the number of k nearest neighbors in your data. So for your point, you have some nearest neighbors to that point, and you just count. This is you just take the just take k and then divide it by the distance to. Okay, sorry.
If you're saying, wouldn't k nearest neighbors always be, the number of that always be k?
Yeah, so it's just k divided by the distance to that.
Okay, the k neighbor. Okay.
Yeah,
Sorry.
just divided by the distance to that k nearest neighbor. And so this would sort of give you so if you think about it in terms of density, this would just be a sphere around your point, and then the density is like how big is this sphere for this specific value of k. And so that would produce a density, a measure of density. And in this case, you would add an edge between 2 points when the Euclidean distance is less than epsilon, and the density is less of these 2 points are both less than or equal to tau. So this is how you would use this. And here's an example of where this is used. So here in the first circle here, we have points sampled without noise from on the circle. And what you can see below here is an invariant, which is called the persistence landscape. And this I will discuss in part 2. But what you can think about right now is just how it changes when we add outliers to this circle. So here in the second circle here, we have added some outliers, and we can see that the information is partially disrupted here. And as we add more and more outliers, we see that the information is more and more destroyed. What we're looking at here is the persistence landscape of the first homology class. So we're looking at cycles. So what we should find for the circle is this one big cycle. And what you should note here is that while the information is of this whole is destroyed, it's not completely destroyed. Like you can see here, it still remains here. That if we have if we filter by high density, then we can still recover the circle. For just usual persistent homology, this information would be destroyed almost immediately. But here we can recover this information even though we have added many outliers. And so a small technicality here, it says co-density, and that's because the density filtration goes in the wrong direction. Because we want to start with a high density and end up with a low density threshold. So we have to flip the x-axis, and that's why we call it co-density. And another example is multi-modal data. So this construction allows you to combine different types of data because we combine different metrics and their information. And so it allows a joint representation of multimodal data that you can study. So an example would be that we let our data set be a set of cells, and we consider one distance to be mutual information of their gene expression, and we let the other metric be the Euclidean distance between their spatial location in a tissue. And this representation will allow us to combine these two sets of data into a joint representation and try to extract information from this. All right. And the third example is has to do with time-varying data. The time-varying data is a bit special because the points are moving, right? And this sort of complicates how you would construct this initial complex, because in how it's formulated, the points cannot be moving, and you have to account for this somehow. And this you can do with multi-persistence, because you can instead. I will give you an example of this in a minute. But using multi-persistence, you can account for this, and you can have for instance, so it will result in a 3-parameter module where you look at time and the Euclidean distance, but time has to be formulated in terms of intervals, and that's why you get a 3-parameter module instead of a 2-parameter module. So constructing the filtration. So I mentioned briefly that there are many ways of constructing the filtration, and I will just give you a formal definition of one way of constructing it. So which is called the Vitroscopes filtration. This is by far the most common one. It's the one usually implemented by default in these software packages for precise homology. But there are other alternatives that may be better for your data. So we start as usual with our dataset X and our metrics that we use to construct the multi-filtration. And we add an edge between 2 points X and Y if the metric di is less than or equal to epsilon I for all I from 1 to R, essentially. So if the two rectangles or balls or whatever metric representation it would have, if they intersect, then we construct an edge. Then we add an edge between these 2 points. And this we generalize this by saying that instead of 2 points, we take a subset of the points, and if these balls or rectangles, if they all pairwise intersect between the points in this set, then we add a simplex. All right. If the set is of size n+1, then we add an n simplex. So, for instance, if we have 3 points and the balls all pairwise intersect, then we fill up the triangle. All right? And this is, as I said, called the Vitroscopes filtration. And this is one of many options. So the options are called check complex, or cubical complex, or alpha complex. And there are, so these are a selection. Okay, so here we can see 2 examples of two filtrations. So the first one constructed using Euclidean distance and a density measure, and the second one constructed using Euclidean distance and a curvature measure. So the density in the first case, it uses this K&N density that I mentioned to you before, and the curvature is so this, I believe, sampled from an algebraic variety, and they have an estimate of the curvature at each point. All right. Is there any questions at this point? Yeah.
Sorry, could you maybe repeat that again? You can estimate the curvature at each point. What does?
So you can either. So I believe in this case that they have some assumption of where the data comes from, and then they can make an estimate of the curvature. So, and you could also estimate the curvature just from the point cloud. I'm not sure how accurate that would be, but that's something you could do. But if you, for instance, would assume that your data is sampled from, for instance, an algebraic variety or some sort of object with structure, then you could make assumptions that will allow you to get some estimate of the curvature depending on the density of your points, etc.
Yeah, okay, so curvature is a domain, sort of another domain depending on the space from which this data is from. It's highly dependent on some parameters, not a persistent homology based.
Exactly. Right, and the second example I will give is for time-varying data. So here the points are moving, which is an issue, but it's a solvable issue. So this can be solved, for instance, by the construction of Kimura-Mimoli, which is based on intervals. So this means that you get a 3-parameter module as a result, and where 2 parameters comes from the start point and end point of an interval. So you sort of look at the space of all intervals, and then the third filtration value comes from Euclidean distance. And this is how you end up with a 3-parameter module encoding this the time-varying behavior. Right. So, are there any questions at this point? Then I suggest we take a break until we make it until 1 o'clock, so 7 minutes. All right. All right. So part 2. Now we will move to invariance of these persistence modules. And in the 1-parameter case, in usual persistent homology, we have this barcode illustrated here, which is a very nice invariant that captures essentially the topological information we're interested in. But in the multi-parameter case, no such thing exists. And this is a problem that has sort of a solution, but it's not. The solution is that we can't get all topological information out of a persistence module in a way that it's computable and visualizable, but we can get some information out, and hopefully that's enough. So for multi-persistence, there is no barcode, and there is no easily visualizable invariant that contains all topological information, because these algebraic objects are very complicated. So that's the thing. It contains a bunch of multivariate behavior that is it's a computational complexity of computing, but also it's not feasible to visualize. And the solution to this problem is simply to only extract information that we care about, or try to, at least. Okay, so here in the multi-parameter setting, there are a number of different types of invariants, and I will give you a selection of examples. This is not an exhaustive list, but there are many more. The first invariant for multi-persistence. So this was the area of multi-persistence is quite new. First paper was in 2009, I believe, and what was also introduced by the same people is also an invariant, which they call the rank invariant. What this invariant does is it simply computes the rank of all the maps in the persistence model. And I will try to give some intuition to this later. What you can also do, seeing as we are dealing with algebraic objects, so the persistence module is an algebraic object, we can just consider the classical invariants for these type of algebraic objects, which are graded modules. And we can look at these classical invariants like Betty numbers, Gäfvert function, and all type of associated primes and things that one would usually study about these modules. But it turns out that these invariants, they don't really translate to the data analysis setting because they are not stable. So if you vary your points, then this invariant could vary arbitrarily, like it's not predictable. But what you can do is you can stabilize these invariants. You can stabilize the Betty number and you can adapt it to this data analysis setting. And this was proved by myself and collaborator Wojtek to be NP hard to compute. So this is not a computable invariant. Another thing you can do is look at what's called persistence landscapes, and this is what we will also discuss later. And Agnese mentioned them yesterday. It's a way of essentially, I will explain it as a way of summarizing the rank invariant, because this is one way you can look at it. And there are other alternatives or other approaches to so persistence landscapes, they in a sense vectorize the information of the persistence module and make it applicable to use with other machine learning algorithms. And the persistent images and kernel methods, they try to achieve the same thing, but in a different way of vectorizing this information. So for the rank invariant. So the definition of the rank invariant is the following. So here P is the persistence module. And so recall that the persistence module, it was this grid of vector spaces, right? So at each position in the grid, you have a vector space, and then you have an arrow to the next vector space, and that arrow is in fact, so that arrow represents a linear map between these vector spaces. And this map has a rank. You can compute the rank of this map. And that's what the rank invariant does. It computes the rank of all combination of maps between filtration values. So here I will give you this example. So on the left here, you see the zero-dimensional persistence module that we had in our example earlier. And it had 7 connected components in the initial filtration value here, which was epsilon equal to 0.2 and tau equal to 0.2. And now what we will do is compute the rank invariant where the first, so epsilon 1, this function, the rank invariant, it takes 2 filtration values as input, so the start filtration value and the end filtration value, and computes the rank of the map between these 2 filtration values. Okay, so if we start at 0.2 and 0.2, so this bottom filtration value here, we will compute the rank of the maps going to all the other filtration values. Okay, so the oh, sorry. So for the first one, we just go from 0.2 to the same filtration value. And this is the identity map. Okay, and so it will have rank 7 because it's a 7-dimensional vector space. And if we look at the filtration value where we set epsilon equal to 0.5, this map will have rank 2 because what happens here, so you don't know what the map is, you just have to trust me, but this you will compute when you compute the persistence module. Then you will know what this map is. But I will tell you what it is. And so here at this filtration value, we start with these 7 components. And then these components get merged, right? They get merged with edges into fewer components, and it gets merged to 2 components, right? And what happens algebraically with this map is that the points that are merged, they are in the kernel of this map. They go to 0 under this map. And so, this map is surjective. Because all the components that live here, they come from points that were in the start filtration value here. So this map has rank 2. And the same type of arguments work here. So up here in this filtration value, where tau was 0.5, we have 4 components. But these components, they all came from the points that were down here, being merged. So this map is also surjective, which means that the rank is 4. And then lastly, we are looking at the map from this initial filtration value here to the top filtration value here, where epsilon is 0.5 and tau is 0.5. And how do we construct this map? We just compose this map and this map, or we can compose this map and this map. So it doesn't matter because this thing has to commute. Like it has to be the same whichever path we choose. Okay. And that's a consequence of how we have constructed this. So it will always commute. So it doesn't matter if we compose this map with this map, or if we compose this map with this map. It will be the same result. And what we have up here is just a single component. Right? We have this component with a cycle in it. It has one hole and a single component. And this component, it's all consistent. It all consists of points that came from down here. So this map is also surjective. So it has rank 1. Okay, and so this is how you construct the ranking variant. And so like a motivation for why this invariant was made and or why it was constructed, and the reason for it's why people use it is because it can be seen as sort of a generalization of the barcode. It's not really, but it should contain like essentially the same information, because if you restrict it to the one parameter case, so usual persistent homology, then it contains the same information as the barcode. So this is an important point. Okay, so if we now just to give you some more information about the ranking variant, now we are looking at the persistence module for homological dimension 1. And if we compute the ranking variant starting at the bottom filtration value here, epsilon equals 0.2 and tau equals 0.2, we will get only zeros, right? Because the starting vector space here is just nothing, it's just 0. But if we instead would have the starting vector space up here, if the first parameter, if the first argument of the ranking variant would be the filtration value up here, then we would get the following result. So below are of course 0 because there's no map in that direction. But we would have the identity map up here. So we would get a non-trivial value here. So the point here is that it matters where you start when you compute the rank invariant. And that's sort of why it contains all the information of the barcode, because it sort of, you can recover the barcode by looking at the ranks of these maps, because then you see when things die and when things appear, and this you can use to reconstruct all this information. Right, so now I will switch to persistence landscapes. And the reason why, or one of the reasons why, the motivations behind persistence landscapes is to construct a space where you have a notion of a mean. Because this you don't naturally have for barcodes. You cannot define the mean of a barcode. It just doesn't work mathematically. So you need to map it into some other space where you have a mean. This will no longer correspond to a barcode, but it will make sense as a mean. Okay? And that's what persistence landscapes does, essentially. For one persistence, the usual persistence, the persistence landscape is what you see on the top here. What it does is that it essentially just associates a pyramid or a triangle to each bar. And then you just look at the intersections of these triangles. That's one way to think about the persistence landscapes. And you can define the persistence landscape using the rank invariant. And that's why I said earlier that you can view it as like a summary of the rank invariant. So I was thinking we could make an example on the board, and we'll try to make this work somehow. Yeah, I'll give it a shot. Does that work? All right, so let's we consider the barcode in the picture, and we will compute the persistence landscape as it was computed as these triangle things. So we will compute the first landscape. So if you see this this lambda here, it takes two arguments, the k, and this is like the yeah, you'll understand more what this is in a minute. But it's for each barcode you get a set of landscapes. And it has to do with how these triangles intersect. This will become apparent in a minute. And then the second argument is the filtration value, which is so this coordinate axis here. So this barcode looks like this. Okay. Alright, I'm hoping that you can see this. And so let's now just compute the first persistence landscape from the definition. So the first bar, it starts here at 3. So let's see what the value is at 3. And so from the definition you see here, what we're looking for is the maximum epsilon. So epsilon is the filtration value, right? The maximum epsilon such that the rank invariant from x minus epsilon to x plus epsilon is larger than or equal to k. So k is in this case 1. And the rank invariant, it computes the rank of this map from x minus epsilon to x plus epsilon, right? And the rank of the map, it just counts the number of bars, essentially. So the number of bars where you started, and how many of those bars survived until the end. Okay. So at filtration value 3, here, we have 1 bar, which is just born. But if we decrease epsilon by just any value, that bar is no longer there. So this, so the maximum epsilon here that we can shift, so this map has some rank, is 0. So here, the value of the landscape is just 0. If we go to the next filtration value, so 4, here we have this small bar here, that's just born, but this larger bar has been born before at 3, and if we consider epsilon, so epsilon equal to 1, which means that we look at the map going from 3 to 5, we see that this bar, it survives during that whole period, right? So we in fact have a map from 3 to 5 of rank 1. But not longer than that because this bar dies at 3. Okay? So here the value is 1. Okay, and so if you go to 5, we see that this bar is just born. This small bar, it's been born at 1 filtration value before, and this bar up here, it has been born at 2 filtration values before. So if we look at epsilon equal to 1, we are then considering the map from 4 to 6, and this map, it has rank 2, right? Because there's 2 bars that survive during this whole period from 2 to 6, from 4 to 6, right? But we can increase epsilon more than that because this top bar is born all the way at 3. So if we choose epsilon equal to 2, we are then considering the map from 3 to 7, and this top bar, it survives all of that. So here, since we're looking for the map of rank 1 or more, and we want to maximize the epsilon, that here the 2 maximizes this epsilon. Okay, so at 6 we get the same thing, that we get some contribution here from this bottom bar here, but that's very little because it's just epsilon equal to 1. We get a map of rank 2. But if we look at the top bar here, we will can choose epsilon even longer. We can choose epsilon equal to 3, right? Because it's born at 3 and it dies at 9. So 6 is just in the middle of that bar. So we can, here we have the value equal to 3. Now at 7, on the other hand, this top bar, since it dies at 9, for this bar epsilon can be at most 2. On the bottom bar, epsilon can also be at most 2 because it's born at 5. So here we have a map of rank 2 from 7 to 9. But we don't have a map of rank 1 that goes further than that, unfortunately. So here it's the value of the first landscape is again 2. But at 8, on the other hand, now we are focusing on this bottom bar. Because here this bar is born at 5, so we can choose epsilon equal to 3. Because 8 is just in the middle of this bar, so here we have a map going from 5 to 11 of rank 1. So here it's again 3. And with analogous argument as before, we're now at 9, so we are focusing on this bottom bar. This we have a map of rank 1 going from 7 to 11, rank 1. And at 2. And here it is 1. And then at 11 it is 0, because here this bottom bar it dies, and so if we increase epsilon by just any tiny amount, there is no longer any bar there, so there is no map, and so it's 0. Okay. Are there any questions on this? Right, then, so what we computed here is what you can see in this picture down here. So it's the first persistence landscapes, which they denote here by lambda 1, and it's outlined in blue here. And this is exactly what we computed. So these are the values that you can see on the board. So it's like this this M here. And this is one way of representing your barcode as a vector, because you can vectorize this this function here. It has we are evaluating it at discrete values, so these discrete filtration values, and the set of filtration values will, in practice, when you compute it, be finite, and so it will be a vector representation of your data in this way. All right. So the good thing about persistence landscapes is that we can formulate a multi-parameter version of them. And here, in the bottom here, you see that now instead of these triangles, you get these pyramid type of things. And you have all the same notions translate. Like you are again you're defining it in the same way, essentially using the rank invariant. You're looking at the ranks of these maps, and you get like the same number of landscapes by looking at the intersection of these pyramids. You're looking at the first persistent landscape, second persistent landscape, but they are now slightly different because they are higher dimensional things. So one thing that's a bit different is that you have a choice of how to measure how to measure the rank invariant, or how to measure these maps, right? Because in the one parameter case, you're just looking at this interval, right? You take x minus epsilon to x plus epsilon. But now you all of a sudden have another dimension to account for. So now you can either look at LP norms for this value. I mean, that's essentially what you do naturally, and you can, and the one that would translate to these pyramids is the L infinity norm. So you have these. So these are just a selection of options that you have, and the difference here. I mean, the definition is essentially exactly the same, only that this epsilon is now a vector. Right? It's no longer just a number, because your filtration value is a vector, because it's something that describes your location in the multi-filtration, and that's parameterized by several coordinates. Right? So now you instead have this vector, and you have to look at the maximal tau that is the norm of your vector that you're constructing this interval with. Right. And if you choose this norm in a different way, you will get different behavior. And the choice which corresponds to these pyramids that I showed you is choosing p equal to infinity. Yeah. Okay, so now I will mention an example now, and then I will mention software, and then that is it. So the example I will tell you about is using these multi-parameter persistence landscapes to distinguish immune cell types. And this is work by Oliver Vipond and Ed Harrington and collaborators. My name is also Oliver, but I am not this Oliver. Yeah, so they looked at these digitized immunohistochemistry diagrams of 16 human head and neck tumors, and they used these multi-parameter landscapes to be able to distinguish these cell types, and they did this by translating these cells into a point cloud, and then using these clustering, so with the Euclidean distance and density, and compute the persistence landscape of this, and then they found that this information was enough to distinguish these cell types. So more specifically, they analyzed the spatial patterns of these cell types, which they were they constructed their test data by staining these slides and annotating them. Pathologists annotated them manually to construct the test data. So the data looked like this. So this on the left here, those are the immunohistochemistry images that were annotated manually to produce the training data. And what you see on the right here are these digitalized point clouds. So this distribution of points corresponds to one of the cell types, which are identified by this CD8 protein, and the And here you see another type of immune cell with another type of distribution, and same at the bottom here. And on the furthest right, you see the persistence landscape. So the first persistence landscape, I think, of these distributions. And this was enough to be able to distinguish between these cell types. So here you can see PCA and LDA plots of these vectorized persistence landscapes. And yeah, for the LDA plots, you can see how it clearly distinguishes between the different cell types. And lastly, I will mention some software for this for multi-parameter persistence. The most used software is called Rivet. It was built as a tool for visualizing the ranking variant. So it's an interactive tool to visualize the ranking variant of 2-parameter persistence modules. So it's restricted to 2 parameters. But it now has other types of functionality to compute different things related to persistence modules. Yeah, so it also has a library to compute, for instance, persistent landscapes and things like this. And we are developing another software which goes under the working title Mufasa, which I'll mention here. So it's library for multi-parameter persistence. So with the goal of making multi-parameter persistence for it to be able to be used in applications. And it's developed together with myself, Michael Lesnick, and Matthias Bender. And it's a C++ library that we have a Python interface for. It implements novel algorithms to efficiently compute multi-parameter persistence modules. This is a complicated problem, but we use techniques from German basis theory to make this tractable for applications. And we, in this software, we can compute all the things that you have to compute for it to be able to be used in an application. So, including persistence landscape. All right, that's it. Thank you.